Imagine, for a second, a world where all those lines crisscrossing above our streets weren't meticulously planned out.
Yeah, like total chaos.
Exactly. Where maybe a tall truck just snagged a vital connection, or a strong wind blew power cables way too close to a building.
It sounds like a recipe for constant disaster, doesn't it?
It really does. Yet somehow, our modern world just hums along day in, day out, pretty safely above our heads.
Mm-hmm.
And the unsung hero, well, it turns out it's a remarkably detailed and honestly surprisingly fascinating set of rules.
Rules that dictate the exact distances for every single wire around us.
Precisely. So today we're doing a deep dive into that hidden rulebook. We're going to explore what dictates how our power lines, our communication lines, interact with everything.
Everything from the ground, buildings, trees.
And even how they interact with each other, right? Our sources for this are two pretty comprehensive tables from the California Public Utilities Commission, the CPUC.
Mm-hmm. One table covers clearances from the physical environment, ground, buildings, water, that sort of thing.
And the other. It outlines all the intricate separations required between different types of wires.
Yeah, the wire-to-wire stuff.
So what's our mission today? We're going to try and pull back the curtain on these really detailed regulations, figure out the logic behind all those numbers.
And maybe uncover some surprising scenarios they've actually accounted for.
Yeah. By the end of this, you should have a much deeper appreciation for the kind of unseen precision that keeps everything powered up and connected safely.
Sounds good.
Okay, so let's unpack this first part. When you look up at utility poles, you probably just see, I don't know, a tangle of wires, right? It's kind of random.
Yeah, that's what most people see.
But what you can't see is this invisible, highly regulated, safety bubble around them.
Mm-hmm. Mm-hmm. And that bubble dictates exactly how far they have to be from everything else in the environment. It's all about establishing these essential safety zones.
Safety zones, okay.
Yeah, minimum distances. From the ground, buildings, roads, even trees. It's all about preventing dangerous contact, keeping the public safe.
Whether you're walking by, driving, working nearby.
Exactly.
And these distances, they aren't just one size fits all, are they? They seem to vary quite a bit depending on the situation and the voltage, I guess.
Oh, absolutely. Voltage is key. And the location. If you look at CPUC Table 1, the ground clearances, it's not just one number.
Right. So, for the normal supply lines, say 0 to 750 volts, the ones maybe powering your house, what are we talking about?
Crossing over, city streets or rural roads, they need about 20 feet of clearance.
20 feet, okay. But then you get those really big, high-voltage lines.
Yeah, the massive ones, 300 up to 550 kilovolts. That jumps significantly. You need 30 feet of clearance then.
30 feet, wow, big difference.
Huge difference. And what really comes out from these numbers isn't just a list, it's this core principle. Higher voltage means you need an exponentially bigger safety buffer.
Right, makes sense.
We're talking differences that, span the height of a person versus a multi-story building, basically. All designed to contain those huge electrical forces.
And it changes based on access, too, right? Like pedestrian areas versus, say, industrial spots.
Totally. In areas that are really just for pedestrians, communication lines can be as low as 8 feet, maybe 12 feet for those 0750V supply lines. Much lower.
Okay.
If those same lines are crossing over railroad tracks, specifically ones carrying freight cars.
Wow, yeah. Much taller potential obstacles.
Exactly. The requirements just skyrocket. That 0750V supply line needs 25 feet minimum clearance there. Enough to clear a tall freight car.
And the really high voltage ones.
Those big 300, 550 kV lines. They need 34 feet over freight tracks.
So the logic is clearly safety first. But are there, challenges in actually meeting these super specific numbers out in the real world?
Oh, constantly. It's always a balancing act, Safety, cost, practicality. These rules are the result of decades of trying to refine that balance.
And it's not just the ground. The tables also cover clearances from buildings and structures.
That's right. Vertical clearance, like above a walkable roof or a bridge surface. For low voltage stuff or comms lines, it's 8 feet.
8 feet. Seems reasonable.
But again, if you've got those 300, 550 kilovolt lines passing over, that jumps all the way up to 20 feet.
20 feet above a walkable surface.
Got it. And even horizontal clearance, like how far a wire just hanging there at rest needs to be from a building it's not attached to.
Okay.
That ranges from just 3 feet for, say, a communication cable up to a pretty significant 15 feet for those big 300, 550 kV lines.
15 feet away horizontally.
Yep. And even the distance from the pole itself is specified, like 15 inches from the center line of the pole for comms wires, or just 3 inches from the surface of the pole for many power lines.
Wow, down to the inch.
These seemingly tiny details, they're all about preventing accidental contact, especially for workers up on the poles or even just the public nearby.
So what does this all mean for you, the listener? Well, it means a truck driver has to think about their vehicle height when planning a route.
Or a construction worker on a roof needs to be really aware of these regulated zones nearby.
Yeah. These aren't just random numbers. They're vital, carefully calculated safety buffers, designed to protect people and property.
Absolutely.
Okay, so we've seen how these rules manage the world around the wires. But what about when the wires themselves get close? The sort of dance they do with each other. That seems like a whole other level of complexity.
It really is. And connecting this to the bigger picture, this part is crucial for preventing interference, short circuit.
Signal problems, maybe.
Exactly. Maintaining signal integrity, especially when you've got such a huge range of voltages and cable types, all sharing the same poles, the same overhead space.
Right. You've got your internet cable maybe inches from something, carrying massive voltage.
Potentially, yeah. And that's where Rule 38 in the second table, Table 2, comes in. It sets the baseline. It says clearances are based on a standard condition, 60 degrees Fahrenheit, no wind.
Okay, starting point.
They can only be reduced by a certain amount because of temperature changes or line loading, which makes them sag. Usually it's a max of 10% reduction.
Only 10% flexibility there.
Or even less, just 5% in certain high-risk fire zones mid-span. And it also clarifies something interesting. Clearances under 5 inches are measured between the wire surfaces.
Okay, the actual outside edges.
But clearances of 5 inches or more, those are measured center line to center line. It accounts for the wire diameter and how they might sway closer.
Ah, that's a subtle but important detail. So this separation between different types of utilities, you mentioned it can be dramatic.
Oh, yeah. Take communication conductors, like your phone or internet line. They need 24 inches of clearance between them and something called span wires.
Span wires, what are those exactly?
They're basically support wires, often holding up heavier cables or equipment, not energized usually.
Okay, so 24 inches, 2 feet from a support wire.
Right. But that same communication line needs 48 inches, 4 feet of clearance from a standard 0750 volt supply conductor.
Double the distance just for basic power.
Yep. And now, get this, from one of those big 300 and 550 kilovolt lines.
Uh-oh.
That communication wire needs a whopping 156 inches of separation.
156 inches. Wait, that's 13 feet.
13 feet, exactly. Between your phone line and a high-voltage transmission line sharing the same corridor.
Wow, okay. That really drives home the point.
It clearly shows the trend, right? The higher the voltage, the greater the required separation. You see it consistently across the tables. It ensures that even if things move around a bit, accidental contact between different voltages is extremely unlikely.
And this isn't just for lines crossing in the air, right? It applies on the pole itself.
Absolutely. There are rules for vertical separation on the same pole, like between different cross arms.
There's horizontal bars holding the wires.
Yeah. So between a communication line on one cross arm and a 0750 VV line on another cross arm above or below it, you need 48 inches.
4 feet vertically on the same pole.
But again, if that power line is 300 and 550 kilovolts, that vertical separation jumps to 147 inches.
147. That's over 12 feet, vertically separated on the same pole structure.
It is. And the horizontal separation on the same crossarm, often called pin spacing, is just as precise.
How far apart they sit side by side.
Right. For 0750 V lines, it might just be 11.5 inches. Pretty close.
Okay.
But for those 300, 550 KV lines, the minimum horizontal spacing on the same crossarm is 150 inches.
150 inches. That's 12 and a half feet.
12 and a half feet. Side by side. Enough room to park a small car between them almost.
That's incredible, just to make sure they don't swing into each other.
Exactly. Even with wind sway or thermal expansion making the line sag, they need that critical distance.
The rules keep evolving, right?
Yeah.
They even cover newer stuff.
They do. The tables have specific entries now for things like uncovered, grounded, non-dielectric fiber optic cables.
Okay, what does that mean in plain English? Fiber optic cables that aren't fully insulated.
Pretty much, yeah. Fiber cables that might have some metallic component or aren't designed to resist electrical contact. They need 15 inches from other communication lines, but 120 inches, 10 feet from those high voltage 300, 550 kV lines.
Huge difference again.
And antennas, too. Antennas mounted on the same pole have their own clearance rules, like 24 inches from comms lines or 120 inches from medium-high voltage lines, say 35,000 to 75,000 volts.
Okay, I found this next part genuinely fascinating
Mm-hmm.
because it goes beyond just static measurements.
Yeah.
It gets into dynamic challenges.
Yeah, these rules aren't just for, like, perfect conditions on solid ground.
No, they account for some really unique situations, changing environments.
Mhm.
It shows an amazing level of foresight, I think.
It really raises the question, how do these rules adapt? Especially in high-risk places like those fire threat zones or over big bodies of water. The level of detail here is, well, it's pretty astounding.
It really is. I had a bit of an aha moment looking at the specifics for waterways. It's not just, clearance over water. That's not specific enough.
Not at all. Table 1, Case 11, it spells it out. For water areas not suitable for sailboating.
Like maybe a small pond or a narrow canal.
Right.
Yeah.
There, it might be 15 feet for communication lines, 25 feet for high-voltage supply lines.
Okay. But then, for water areas suitable for sailboating.
Huh? This is where it gets really interesting. The clearance is very wildly based on the surface area of the water body itself.
Get this. For lakes or areas less than 20 acres, the clearance range is 18 to 27 feet.
Okay, manageable.
But jump to a really big lake, over 2,000 acres.
Yeah.
Those clearances soar to 38 to 47 feet.
47 feet. Almost 50 feet of clearance needed over a large lake suitable for sailing.
Incredible, right? And the notes even clarify how to measure. For reservoirs, it's based on the high water level.
Makes sense.
And for rivers or streams, it's based on the largest surface area you find in any 1 mile stretch, or the bigger body of water it connects to, if that allows sailboats in.
So yeah, next time you're out on a sailboat, you can appreciate the math that went into ensuring those power lines overhead are high enough, factoring in the size of the lake, potential high water.
The height of your mast.
Yeah.
It's this invisible net of safety calculated with incredible precision.
It truly is.
And speaking of critical safety, let's talk vegetation, especially in California with the fire threat districts. This is huge.
Absolutely crucial. If you just look at the general rule for radial clearance from tree branches, outside of those specific zones.
Yeah. What is it normally?
It can be as low as 18 inches. For communication lines or even for supply lines up to 22,500 volts.
1.5 feet. Okay.
The second you're inside a designated high fire threat district, those requirements get much, much stricter.
How much stricter?
Significantly. For 0750V circuits, they need 18 to 48 inches clear of vegetation. For the medium voltage lines, 22.5 up to 300 kilovolts, that jumps to 48 to 120 inches.
120 inches. That's 10 feet of clearance from any vegetation for those lines.
10 feet minimum radial clearance in fire zones, yes. And for the highest voltage, 550 kiloV. It's a flat 120 inches minimum.
Wow. That's a direct response to preventing those devastating wildfires caused by lines contacting trees.
Absolutely. It's a major focus. And there's even an interesting exception noted. These really strict fire zone clearances, they don't apply to like cultivated orchards, fruit trees, nut trees, citrus groves.
Because they're actively managed, trimmed regularly.
Exactly. The rules recognize that difference. In those managed orchards, the general, less strict tree clearance rules apply.
That makes sense. So it really isn't just a fixed distance. It's more like a living, breathing safety margin.
That's a great way to put it. It adapts to specific conditions, potential hazards. And
it also accounts for those dynamic forces we mentioned earlier, right? Like temperature and wind.
Yes. We talked about how the rules allow for that small reduction, maybe 5% or 10%, due to temperature or loading making lines sag.
Right.
And the notes explicitly mention high winds. They say, in areas that are subjected to high winds, a utility may need to take extra measures.
Like what kind of measures?
Things like installing spacer bars between the lines to keep them from slapping together, or increasing the pin spacing, that horizontal distance on the crossarm, even beyond the standard minimums.
So it's constantly being evaluated and adapted.
Mm-hmm.
It's really this amazing intersection of engineering and regulation, always evolving.
Precisely.
Well, as we wrap up this deep dive, it's just so clear that this whole world of utility clearances, it's far from boring or mundane.
Not at all. It's actually a testament to incredible precision, incredible foresight.
And just a profound commitment to keeping the public safe.
Yeah. These tables, they might look dry, but they're really a foundational layer of our entire modern infrastructure.
Quietly ensuring reliability for power, for communications.
And preventing countless potential accidents and hazards in a world that's just getting more complex and more electrified all the time.
So, Next time you see a power line, whether you're driving under it, walking near it, maybe even boating beneath it,
Mm-hmm.
it's not just hanging there by chance.
Mm-hmm. It's positioned with incredible intent.
Following this meticulously crafted set of rules, keeping everything humming along safely right above your head.
That's the goal.
So here's something to think about. What other hidden rule books, what other unseen engineering marvels govern the infrastructure we rely on and maybe take for granted every single day, keeping our modern lives running smoothly?